Welcome to Oscilloscopes Part 1. The first thing we'll talk about is the test leads themselves. Notice how they are neatly and loosely coiled without twists or memory in them. Very simple but very important to maintain your test leads. For example, when you're putting them away, and you're going to have to, just follow the leads themselves. I like to, stretch them out, and I know the camera's not zoomed out enough to see all this, but stretch them out. If there is any twist, let that twist sort of naturally come out of the wires. Just sort of guide them, with your hand. Just sort of take them and let the leads themselves untwist, and then lazy loop them into some nice easy loops. And look, again, I know the camera's a little out, but let the wire find its own path. Don't force it, because that forces twists into the wire. So what I'm doing is I'm just letting the wires tell me how they want to be put away. And that way you don't keep building twists into the cable. You'll see cables that are well maintained, they still look straight. They don't look all twisted and mangled. And it's very important because the metal in the cable can only handle so much of that before it does start to break. So you want what I call lazy loops. You want to take what's called the memory out of the cable just by letting it untwist itself. Gently sort of move the wires back straight while they untwist themselves. And then you shouldn't have to force any any twisting, but you should be able to, put them away, something like this. I will be checking the benches every day. I always do, just to make sure everything's off. One of the things I look at the most closely is I want to see good test lead maintenance. Definitely lose lab points. I just find that irritating if the leads are not put away that in a way that maintains them. They are expensive. I mean, they can be $100 per test lead, and so partly why it's aggravating if they're not put away properly. So do that. It's a simple thing, but take the time to do it, and we'll keep the leads from breaking that way. These are 4-channel scopes, so we have 4 leads. So I tend to group them in 2 because sometimes you're only using 2 channels, and it's just a little easier that way to have to not untangle all 4 all the time. And I do want to show you how not to wrap them up, right? This would be forcing the wire. Like if I took my hand here and I just wrap, this is not good at all. Look at me. I'm just like twisting it like crazy and wrapping it around my finger. And I hate to even do this once. Don't do this. Okay, this is the how not to put a cable away. Do you see how it sprung away from that? It did not want that. But I was forcing the twist around my hand. Don't do that. Don't wrap them up. We call that maybe wrapping it up. And if you've ever worked in any place that has you put away cables, that's not how to do it. Look what happens, right? It's just a jumbled, snarled mess. And maybe that's not a bad picture, right? This is how not to do it, right? So when I see that at your bench, going to cost some points there. And remember, this probe maintenance is not something that you're doing for me. It's something you're doing for the cables so that they stay reliable. And of course, that serves you as you do your labs and your lab test, of course. An oscilloscope is an instrument that reads voltage and displays it in time. So you can think of this 4-channel scope as really 4 voltmeters with the added ability to display voltage through time, so we can see all kinds of changes. So it's one step up from your actual handheld DMM voltmeter. To connect the probes to whatever voltage you want to look at, you simply pull this little spring-loaded plunger down. You've got a little mini grabber hook on the end that you can hook on to any point in the circuit. Some people like to even hook onto a little wire and then use the wire to probe. We're going to have our medium breadboard set up where we can actually receive that hook right onto a little tab. But yeah, there's different ways you can hook to the circuit. We can even pop these off and you can probe with the point, but let's not do that. I don't want to be putting these on and off and all that wear and tear. Really, we just need the, the mini grabber hook for our connectivity. And we said this is basically a voltmeter in some ways. And so, of course, we know to measure voltage, you can't measure voltage just at a point. Voltage is the difference between 2 points. What is the other point? Well, there is a common for the scope. And in fact, there is a ground clip that attaches to the probe. If you want to do it this way, it clips on here. We actually will be doing it a different way, but I'm going to show you this. This is pretty standard. So what's happening here is for this channel 1, we'll measure the voltage at the probe tip as it compares to this wherever you connect this ground clip or this common for the scope, that clip. Now, in fact, every probe has the ability to connect a ground clip to it. And so I've done that for channel 2. So now I have a ground clip for channel 1, a ground clip for channel 2. Very important that you understand these ground clips are the same point. Yes, there's 2 different clips that I could hook up to 2 different points in the circuit, but if I do that, I will short out whatever is between these 2 clips. They are the same point electrically, and if you needed to check that, you can always just put your ohm meter across them and you'll see a 0 ohm path, meaning these 2 clips are the same. So you must always connect them to the same point in the circuit, which kind of makes you probably wonder, why do I need 2? Well, you don't. I mean, you can take this one off, and in fact, once you have the common connection for the scope made to your circuit common, all the probes will measure circuit voltages at their probe tip with reference to circuit common. You just need one connection, in fact. So why did they give you 4 clips? Because in fact, when you get these scopes, you'll have these ground clips attached to each probe. And the answer to that is sometimes you need that ground to be real close to where the probe tip is if you're trying to do high frequency measurements, or if you're trying to do real low voltage measurements where noise is a problem. Then sometimes the short ground wire helps with that. For us, we're not going to use these ground clips, at least unless we need them. They tend to be unnecessary for a lot of the simple circuits we're doing, especially in the beginning. So what I want to use is yet another connection point on the scope, which is also scope common, and that sits right here. You can see the little grounding symbol. So what I want us to do is use our little mini grabber to mini grabber test lead in your toolkit and just hook on to scope common right here. Okay, and that will be where you make the connection to your circuit common, and now voltages that you measure on channel 1, 2, and 3 will just be referenced to scope common right here and circuit common. So that's our common connection that we'll use. We won't use the ground clips. We don't need them at this point. The probes connect to the scope through what's called a Bnc connection. And let me just show you that. So these will come off. You have to twist. There's like a little twist lock mechanism. And there's some keys here that have to line up. Don't force anything ever. You're doing something wrong if it doesn't go on easily. But you're just going to... they're probably already attached to your scope, but if you needed to unattach them. And there's a little spring-loaded here mechanism, and that'll just twist lock right on, okay? Also on this end of the probe, there's a little adjustment screw that we'll be using in a few minutes. And so what you need is this barrel here can rotate it to a position where you can have access to that with a little screwdriver that's provided. Don't just use this one. This one's intended to fit, and you want to very carefully, you know, without too much pressure, but find where that slot lines up. You know, just kind of rotate it gently, you know, just between 2 fingers. You don't want to put a lot of torque on this. It's easy to break it. What that is, it's a variable capacitor, just like we know variable resistors. There's also can be variable capacitors. We'll study caps later. But that's what it is, and it rotates, and you just have to be careful. If you would over rotate it with too much force, you can break it. So you just have to be real careful with that. Be gentle, know where you've aligned the slot, and then we'll be doing this adjustment in just a few minutes. When you attach the probe to the scope, you'll see first you have to get that Bnc connector twist locked in place, and then if, for example, this adjustment hole that where the trimmer cap is, if that wasn't available, if it was facing down here at the bottom, you can rotate this barrel of this probe. Just be careful, all of this is fragile. You don't want to overdo things and break things. But you can always rotate that if you needed to, so that you have access to adjust it. And finally, at the other end of the probe, we have one more thing to look at, and then we'll actually do the whole probe setup with the scope. So the other thing to look at is a switch, and it's a little selector switch, and it might be hard to see, but it's marked X1 and X10, which means you can select that with the switch. If I put it to the ×1 position, that means I'm not attenuating the signal at all. In other words, if there's 10 volts at the tip, at the probe tip, 10 volts will go into the scope to be read. If I throw this to the ×10 position, it means it's going to attenuate it 10 times, not multiply it. So it's going to be 10 times less on the 10 times position. In other words, if there's 10 volts at the probe tip, only 1 volt's going to be received into the scope. Okay, so that's very important to always keep an eye on where your selector switch is for your probe, because the scope has to be set to match that. Otherwise, your numbers are off by a factor of 10. Which is a good clue. If your numbers are off by a factor of 10, you might have bumped this switch without realizing it. That's a quick clue. The thing that switch does, as far as, I mean, when do you choose, where to put it? Well, remember for voltmeters, because that's what we have here, basically a voltage measurement. Remember, the ideal voltmeter is infinite ohms or infinite impedance, so the higher the better. And what happens on the 10 times setting, your input impedance, or kind of your resistance, we haven't learned totally what impedance means, but your 10 times setting puts 10 megohms of impedance for your voltmeter for your scope input. Okay, on the 1 times switch setting, it's only 1 megohm. So 10 megohms is better than 1, so we like the 10 times setting if we can use it. The times we might not use the 10 times setting is if the voltage that we're trying to measure at the probe tip is very small. So if it's maybe 100 millivolts here, putting it on the 10 times setting is going to knock that down to 10 millivolts for the scope to try to read. So that's not ideal. We'd probably just go with the 1 times setting, even though we only have 1 megohm. We don't want to knock that small signal down even lower for the scope. What that does is when the scope amplifies it, it'll have to amplify it a lot, which amplifies the noise too, because noise tends to be in the millivolt range, and it'll get amplified along with that small signal. So yeah, so low level signals, you might put it on 1 times. So let's turn on the scope, and then we'll show you how to actually do the probe setups for each channel. Here's the power button, of course. Okay, well, there are a lot of controls, a lot of adjustments, a lot of capability in these scopes. So what we're going to do is just try to chip away at it, just try to show you a couple controls at a time, and to do what we need to do. So to get started, I guess we're going to finish the probe setup, and I'm going to put the channel 1 probe on the 10 times setting. You don't need to do the adjustment for the 1 times setting. It doesn't use the variable capacitor on that setting. What I'm going to do is hook it to a test point here. So I've got my channel 1, and I'm going to hook it right onto this little test pin. That puts out a 2-volt square wave, and a square wave just is a voltage that goes high and low. Now, nothing shows up on the screen while I don't have any channels turned on. So here's channel 1, just push the button. I've got channel 1 on. And we see that square wave, although it doesn't look real square, and that's why we have to do the adjustment, okay? So what the adjustment is to get in here on this trim pot and rotate it, and I'll show you. This is called probe compensation, and I'll show you if I get it. You got to get it in the slot there. Okay, now look, that's one direction. I'm going the wrong way. Now I'm looking like a square wave. That looks pretty good. If I'm undercompensated, I'm going the other direction. Gotta be careful here. So that would be bad too, right? So you have to be able to figure out where the square wave looks like a square wave, okay? Now you might not have gotten a square wave up on your screen that looks like this, and that's some of the settings I'll have to show you quick. For one thing, this trigger knob sets a point for the scope to synchronize to. And so right here is a little arrow, a little cursor that shows that the scope is watching for a voltage level there. And the problem is if I have this trigger level telling the scope to watch for a voltage level that never occurs, as in down here, it can't synchronize itself to the signal. So that's why I'm getting that roving display. It's not standing still. So that's something to always be aware of, that your trigger that you're telling the scope to watch for has to be obviously a voltage that actually occurs. Likewise, if I went up too high, you can see I'm asking it to watch for 300 millivolts DC on a rising edge. Well, that never occurs. So the scope has to have some point that you describe for it or set it for to synchronize itself to that point. And you can see this cursor tells you time 0. This is the event that the scope watched for, and this is time 0. So it saw the voltage go through 104 millivolts. Well, I got something there, huh? I don't think I have my probe matched, right? Because I'm thinking to myself, 2 volt signals what I'm supposed to be getting. This is that factor of 10. So let's fix that before we confuse you entirely on that. Look, my probe voltage is set for 1 times, but I have the probe switch at 10 times. So let's fix that before we get even more confused. I don't know if you can see the 1 times. It's hard on this video, but this says 1 times. When I press this button, it gives me options. I guess it's going to take me up to maybe this knob up here. I'll try that knob 2 times, 5 times, 10 times. Well, I like that one, so I'm going to keep that. Now it shows up as 10 times. Now I'm not getting that weird, 100 millivolts or 0.1 volt. This looks more like it, right? My trigger level that's giving the scope a valid voltage to synchronize itself to is reading, it's watching for 1 volt on a rising edge. I don't know if you probably can't see that little icon. But again, this is difficult with video, I'm sure. But here's my cursor, and it's sitting 1 block up, which means that there's a volt there. Okay, now that I have my focusing under control, this will be a little easier to show you some things. So here is the trigger display. It's telling me that I'm watching for 1 volt on a rising edge coming in on channel 1, and it's a DC voltage level. It's sitting 1 block up, and I can mention another knob here. This scale knob right here is what sets how much each square is worth on the scope grid in the vertical dimension. Right now I have it so that channel 1 is set for 1 volt per division. That means each square is worth 1 volt. And that makes sense because my trigger level is at 1 volt. So that kind of agrees with that. It also makes sense because they said they were going to be providing a 2 volt square wave, a 2 volt peak square wave for the test signal. And look, 2 volts. There it is. That scale, vertical scale, is right here. I just made it 2 volts per division. See where that took the display? I think it's obvious, but it's important that you understand I did not change the signal itself. I changed the magnification for the display. So there it's back. I could take it to 0.5 volt maybe. Now I'm only 0.5 volt. It's right at the top. So that's 0.5, 1, 1.5, and 2 volts, and so on. So that's the scale knob for channel 1. Position-wise, I can slide the 0 volt position of that waveform wherever I want, and this cursor marks that. So this is a 0 volt position, and we can slide it. If I wanted to put it and display it somewhere else, I can do whatever I want with that. Now 0 volts is here. It's still 1 volt per division, so 1, 2. So this cursor always shows you where 0 volts is, and we'll get to it more, but this cursor tells you where 0 seconds is. And it does pre-record data up to the synchronizing point and after. But that's time 0. I can slide time 0 around too if I want to. That's this position knob here, so I can move the display all over the place, right? I can put time 0 wherever I want. Put it back to the center. So on. And another thing, now we better look at a bunch of these controls. It's hard because you need to know a bunch of them to even get this display. This display might not show up for you still. Maybe you had the trigger off, for example. Okay, well that'll make it stand still for you. But let's look at some other things that you might have to set. Here we're talking, we need it on DC coupling, and that's an option that we'll talk about later. If I go to AC coupling, it blocks the DC. Ground just grounds out the channel. So DC, now that doesn't mean you're measuring a DC waveform, DC voltage. It stands for direct coupling. Direct coupling shows you everything. So the rule that we'll use is always put it on direct coupling because you always want to see everything that's there. Unless you have a good reason to use AC coupling, don't use it. And there are maybe 2 or 3 reasons that we'll run into. But for now, DC coupling. And what else? We could invert the waveform, but no need. Let's leave that off. That just flips it upside down. Bandwidth, we don't need the full bandwidth. We're looking at low frequencies. It doesn't hurt. What this does for you is let you throw away really high frequencies that tend to be, that's where noise lives in a lot of times in the higher frequencies. So you can sometimes get rid of some noise. We probably might as well show you. I mean, for our channels, this is all the channel setup menu. 20 megahertz, we're not going to be going above that. So we can go with a 20 megahertz bandwidth limit. That's fine. And let's see what else is important. So these all look good. So that looks good. So those are the main ones. I mean, we can use bandwidth limit, DC coupling 10 times. That's a big one, right? Because we're doing the probe setup. So remember, that's the setting that has to match the switch on your probe. And here's a little button that you can use to clear the menu that's on your screen, so we get back to a clear screen. So again, just notice your cursors. That cursor tells you where the trigger level is, and it has to be a spot that actually occurs in the incoming signal. Of course, there's time 0 and there's 0 volt level preference. And I know it's a lot of buttons and knobs, but look, I guess those are the 3. Now let's look at some these 3 we'll use to set for now. We'll talk about other ones later. Let's talk about other reasons you might still not see the waveform showing up. Let's assume you had a trigger level in there, but you might see something where if you're scanning too fast or too slow, let's show you what that looks like. And that has to do with the scale for the horizontal scale, which is really telling you how many seconds each square is worth. So I can use this scale knob to sweep across the screen faster or slower. Now I'm scanning really fast, and look, I don't see anything, but it's because I'm zipping across the screen so fast that I'm only seeing a very little piece of the waveform. Okay, so I have to slow it down. Like right now, it is the scale, the horizontal scale is 200 nanoseconds per block, so that's really fast. So let's slow it down. Now it's 2 microseconds, now it's 5, 10 microseconds, and so on. All right, keep slowing it down. Now we're seeing a waveform, right, that we want to use. But so the magnification, you could think of it that way too. It's kind of magnification settings for the scale. You can set the vertical scale here, you can set the horizontal scale here. Look what happens if I'm scanning too slow. I just get sort of a lot of, clutter, right? It's just because I'm going way too slow, right? And so, yeah, the signal's coming in. It's going high and low, but I'm just moving so slow that it just paints the whole thing in. So speed it up, okay? Yeah, and there we go. So those 2 magnifications are really important. If I go really slow, yeah, other things happen with, we'll talk about that. You can get an alias on the screen if you're scanning way too slow. Save that for another time. So we pretty much have the probe set up. We did do the probe compensation. That was the main thing, and we had to learn a couple controls to do that. I want to show you, though, you can even maybe do a little better on the probe compensation if we use the magnification. So let me do this for you. I'm going to take the positioning of channel 1 down a little bit so I can have more screen to work with, and I'm going to blow it up a little bit so you can see I'll have a bigger picture to work with and maybe a more accurate picture. So you'll hear me say a lot bigger is better with scopes and with anything. I mean, you make it large and then you can see better resolution and see how well you're doing. And it looks like we did pretty good. I mean, even with it blown up to a bigger size, it still looks pretty square. I could maybe adjust it a little bit. But I'm going to do one more thing. And that is there's an averaging function that will probably even clean up the noise. We have some, wherever it's a little bit thick there, that's a little bit of noise coming in. Averaging tends to get rid of noise because noise tends to be random. So if something is randomly high and low, when you average it all together, the net is 0. And that's a trick we use to get rid of noise. And that ability is up here at the acquire button. So if we push that, it'll bring up a menu where we can pick, let's see, I think it might be here. Let's pick the mode. I'm picking this button. Let's see where that takes me. Okay, so I can either read every sample as it comes into the scope, or I can choose to maybe average 4 readings together. And that should clean up the signal. There's times to use averaging, like for measurements, but it does hide the truth from you. So when you average a signal, it's not showing you the real signal that's there with all the ugliness. It cleans it up, but falsely. So keep that in mind. There's times to average, maybe you're going for a measurement. There's times to not average because you need to see what's actually there. Okay, so let's go ahead and try the averaging. And right now, it's you see how it cleaned it up a bit? It's taking 4 samples and averaging them together. If I increase the number of averages, it might even get more of a pencil line. At some point, you're averaging and it doesn't really make too much difference. But whatever, maybe 16 or 8. It does slow down the acquisition though, so you always have to remember you're going to now take 8 readings and then display it. Going to take 16 readings now and then average them and display that result. I'll go with 8, and it did give me a nice thin line to work with, which I like for my probe compensation, although it seems like we did pretty good even without magnifying it and doing the acquiring, the averaging. Let me get this off of here. But now you can see if I was going to fine tune it, if I wasn't happy with it, it looks pretty good. But look, my adjustment now for my probe should be a little more, I could make it even more precise. Let's see if I can get that. Okay, so there you can see I want it right. Yeah, that looks pretty good. And if I went the other way, of course, that's too far the other direction. So this is if you want to get more precise. Obviously, bigger's better. Averaging also helps with that too. Get you a nice pencil thin lines. Don't forget, in channel 1's menu, I'm just going to hit the channel button, and when I hit channel 1, it brings up this menu. The other thing that helps us get nice clean lines is it helps a little bit, this bandwidth limit. Remember, we threw away everything above 20 megahertz because we're not really interested in measuring anything above that. We're way below 20 megahertz. So that's what the bandwidth limit did for us. So that's another way to help clean up waveforms. It gets rid of noise above 20 megahertz, which we don't care about anyway. We don't want to see that signal. And then the averaging is the other thing that got rid of noise. A little bit, like we say, a little bit falsely. I mean, it's there, but we just averaged it out. And now that I've got the probe compensated, I am going to take the averaging off because for other things I want to watch, I want to see how noisy they are as a point of interest. I mean, if it's a really noisy signal, I want to know about it. So I'm going to take this, I'm going to go up to the acquire button here. And remember, see, it shows me that it's in averaging mode. And that's highlighted. So I'm going to head to take it back to just sample mode, which will be this soft key here. There we go. Now it's showing sample mode, and I think we're good. Yeah, sample mode. If I want to get back to my channel menu display, I just hit the channel button. I'm back to this display here. Some of the highlights you can see are, I mean, you can see I took averaging off, right? I got sort of that thicker line now again. And looks good. DC coupling, bandwidth limit, 10 times, because I'm using the, I have the switch on my probe set for 10 times. So on. And the heads-up display, which we see here from the channel menu by pushing this button, let's just kind of look at all the little things it tries to help us see at a glance. It's telling us the coupling, DC coupling, but look, it also tells us the vertical scale, 500 millivolts per division. It tells us whether it's inverted or not. It's not, it's off. Bandwidth limit's on by ground or by center. We want to just be off of ground. You can play with that, but it's not a big deal. Here's even the vertical positioning. It's telling us that we have the cursor, the 0 volts is sitting at the negative 1 volt off of the center of the screen. So I mean, but you can see that here with the cursor. You could see it here too. Incidentally, if you it's telling you if you push this position button it'll zero it. It'll take it right back. Notice what I did there. So it was sitting 1 volt off of center, negative 1 volt, and then I press it and it jumps back to the center of the screen. I mean, just a little feature, but I don't have to use it. So there I had it. And then, of course, your switch setting on your probe 10 times is sitting here. It's hard to see. I know it's washed out. This little heads-up part of the display of the heads-up display is the horizontal position. It's telling us 200 microseconds per block is the scale, and it's telling us where our time 0 is on the screen, and it's at 0. But I mean, again, I can move it positionally. I could slide time 0 over, and it's telling me where I'm at now as far as this with reference to the center of the screen. And again, if I want to center, I can just press that button and it zaps it right back. And finally, this heads-up display gives us the trigger information, which we'll have to, I know, probably do another video on triggering, but we can go to the trigger menu quickly here, I guess, but it's giving us the short notes on it. It's telling us we have the triggering, which is really, remember, how the scope synchronizes itself to the signal that it's trying to display, because it has to overlap the signal at the same point, otherwise you'll just get gibberish on the screen. So it's watching for a signal coming in on channel 1, it's watching for 1 volt to occur on a rising edge, and then it's going by that. And it's telling us here that it sees that event happen 1,000 times a second. 1 kilohertz is the frequency of the trigger that the scope has picked up on. And let's go to the trigger menu. Why not? I mean, real quickly, we could take a look. Here is all the triggering section. If we pull up the trigger menu, you can see you can choose. And edge triggering is probably, we'll use that the most. I don't know what else do they have here. All different ones, pulse triggering and stuff. Edge triggering, and then you can pick are you watching for the signal coming in on channel 1 or something else, channel 2, channel 3. So you can pick what channel you want. If I wanted to, I could come in on other channels, just here. Couple it, yeah, bring everything in. Here's the slope. Watch, if I go to pick a negative slope for triggering, it will look, you'll see, well, let's just do it. Look, now it's watching for that same 1 volt occurrence, but on a falling edge. So here's time 0, and there's the trigger event that it saw, that it's going to synchronize itself to and overlay the picture based on that point. Yeah. And so let's see, there we go. Rising edge, I have it on rising edge. Sometimes you need the falling edge. I mean, if you want to examine one edge or the other, yeah, and magnify it, you'd have to be on that edge. It's telling us the level. Of course, that changes with this knob here, but it's just a little heads-up display on where your level is. And that's already given to us in the channel heads-up display, right? So we'll talk about this. This is really important, but it's probably for another video. Auto mode or normal mode. Auto mode is the scope going to sweep. It's going to sweep and paint a picture whether a trigger signal is present or not. but in normal mode, it will only sweep if it sees a trigger. So there's a distinction there that you have to really understand. If we went to normal mode and we took the trigger out of the picture, it's not going to keep sweeping. It's going to freeze. We'll talk about that more later. Normal mode is where you want it a lot of times if you're just trying to find the signal, because otherwise it'll be a blank screen until you find it. So in auto mode, it scrolls no matter what, and you make sure it stands still by putting a trigger that's valid into it. I know, lots of topics. We'll try to keep chipping away at them. So let's go ahead and clear this menu. Remember, this button will clear. It'll clear again, clear everything off. This is just sort of the main points of your display, right? I mean, there's a channel display for channel 1. If I turn on the other channels, of course, they'll show up there too. Let's turn them all on. Why not? Get that off of there. See how you have your scales for each of the channels. I'm not necessarily believing these. We didn't set up those probes yet. I'm wondering if they're going to wind up being 1 volt, right, per scale. But that's up to us, the operator. We have to tell the scope if we're on the 10 times or the 1 times, you know. So I suspect if we go to channel 2's menu, where was it? Here we are. Yep, we're on 1 time. So we got to set all those, right, to 10 times. Oops, there we go. Let's go to channel 3's menu, and then we'll see the 10 times. We're going to have all our probes set for 10 times. Channel 4's menu, set them all. There we go. And now you can see we have them all set up for 1 volt per block. And there's no signals coming in on the other channels, so they're all just tracing down the middle. For this video, it's all about the probes and setting them up. So you would want to do probe compensation for the other 3 channels, 2, 3, and 4. Get those all set up. And of course, you can then bring in and display more than 1 channel at a time. You can display all 4 channels if you had that many signals you wanted to look at. Probably for our beginning exercise, we'll just look at 2 signals perhaps, and then go from there. Any channels you're not using, of course, it's nice to turn them off. That way they're not just tracing across the screen with a straight line. Let's quickly set up channel 2, and then we'll show you a quick little exercise we'll finish with. So unhook channel 1, right? Get channel 2 on there. I'm going to set channel 2 for 10 times. Don't forget to do that, right? The little 10 times switch there. So we got that back at the 10 times position. Hook it on. If you're wondering why we don't need the ground clip, the scope already has that reference internally. So that's why we don't need to hook anything on there, obviously. Okay, let's get channel 1 off the screen. Let's get channel 2 up on the screen. I'm getting this. Well, time to go to work, right? So let's see what we've got. We got DC coupling. I'm going to take the bandwidth down to, I decreased that to 20 megahertz. I'm not interested in anything above that. I do have the 10 times already set, so that's good. Let's see. Oh, I think I know what I got to do next. Do you have any ideas? Why is the triggering not working? So in other words, the scope cannot seem to synchronize itself. So it's just randomly displaying the voltage that's coming in on channel 2. It is displaying it, but it's having a hard time picking a point on which to paint the picture over top of itself over and over again so that it stands still, essentially. Why is that? Let's go to the trigger menu, because I'm suspecting that it's a triggering issue. And we're going to go to the menu here. Right away as I see something, and you might not know to recognize it, but look, I see a yellow cursor for triggering, which means the triggering for the scope is watching channel 1. And channel 1's not connected now anymore to anything. So that's why it can't find a good trigger signal to synchronize itself to. And in fact, all this is showing me that too, this heads up here. It's like saying, hey, look, you're looking at channel 1. So let's change that, obviously. We still want edge triggering. That's good. The source is what we have to change. We'll still go with a rising edge. We can still go with, we're at a 1 volt level. We're just looking at the wrong channel. So let's go to channel 2, and everything should snap into place. Here we go. I notice you have to use these soft keys, and then you also have to use this sort of universal knob there. Things are looking better. Let me get the menu off of here, get it out of my way. Okay, so I can do probe compensation. Looking at a couple things here. I'm looking here. Okay, it's set for 0 volts. Well, I don't like that I'm dancing on the edge of the signal. I want that trigger to be able to be somewhere in the heart of the signal where I know it's going to be reliable. So I'm going to move this trigger level up. A 1 volt level is perfect, right? On a rising edge of a 2 volt peak signal, I'm right in the heart of it. I'm right in the thick of it. So that's going to be a reliable spot to trigger off of. And I just got to do my probe compensation. So let me get my little screwdriver here. And that knob's right in my way. So I'm going to I'm going to rotate this barrel a little bit, you know, wherever I can, if I can. Oh, here. There we go. Oh, so it wasn't really in my way. I was looking at the wrong spot. But all right, so let's get there. Again, you have to gently find the notch where that'll drop into, and then let's see if we can turn this. Try not to force anything. There we go. And I noticed this one does turn a little bit. It's pretty stiff. It's a little tough. Okay, so where am I? Okay, so there we go. That's looking pretty good. Of course, if I wanted to be more picky, I could expand things, right? I could blow that up. Whoops, wrong scale. Channel 2 scales there. Went off the screen. I can bring it back by positioning 0 volts somewhere. I have more screen to work with. If I drop the positioning, you know, if I wanted to go to the acquire just for practice, the acquire button will bring up the option to jump out of sample mode into averaging mode. Get that pencil thin line. Not that I need it, but just for practice. And I can, while I'm there, be a real perfectionist here if I want to, but yeah, not necessary. Mostly I'm doing it just for practice. Okay, let's go back to sample mode though. Okay, let's get this off of here. Looks like we're ready to go. So we've got 2 channels. You can do the other 2, 3 and 4, and then let me set up a little exercise to let you maybe at least try something. Okay, so just to finish up, let's see if we can get something from the outside world to show up on our scope. And we'll just keep it real simple as we're just in the beginning stages of being able to drive this thing. So let's take our little breadboards. We've got them, the batteries in series 8, so we got the 3 volts. That's this jumper. And then I've created a little voltage divider with a photocell and a 10K resistor. And that's going to be the 3 volts is going to be applied to that voltage divider. I also have a 1K pot, and I've applied the 3 volts across the fixed resistance of that potentiometer so that I can get a variable voltage out at the wiper of 0 to 3 volts. And to get the probes attached to this circuit, I'm just going to use these little jumpers here. So do yourself a favor, color code them. Makes it easy to see what you've got connected where. Of course, the ground for the scope has to be shared with the common for the circuit. So the scope common and the circuit common have to be the same. So let's make that happen. And let's see. This is my circuit common. Ooh, see if I can keep that circuit up there. And channel 1 and channel 2. Well, I'll have channel 1 watch the output from the voltage divider with the solar cell. With the photocell in it. See if I can keep that circuit from falling off. Okay, that's going to go right there in the middle of the voltage divider, right? And now I'm watching the voltage really across the 10K resistor, right? Let's see if I can get channel 2 on here. See, here's channel 2's clip. We're just using, like I say, these little jumper wires work fine for what we're doing. I got to get that right to the wiper of the potentiometer. Okay. Well, I think I have it all connected. And now, with the scope, we'll have to, see what we need to adjust. Why don't we do this? Why don't we put both of them on the, center both of them, I guess. We can do that. I'm doing that because I'm going to compare the 2 voltages, so I want them to have the same positioning on the screen. What do we want? Let's do this, and for that reason also, let's make the scales the same. So I'm going to make channel 2 also 1 volt per division. So channel 1 is 1 volt per division, channel 2 is 1 volt per division. And now I'm going to actually show you another sort of mode for the scope. I'm just going to go really slow. So I'm going to take it down to super slow-mo, right? And here's the scale for how fast I'm scanning. I'm going to just let this trace across so I can see what's happening in real time. See that? Let me try my potentiometer. I should be able to move it from 0 to 3 volts, right? And if I look at my screen, I can see what I'd predict, right? Both channels are 0 volts is at the center of the screen, and they're both at 1 volt per division. I can see what? The pot output right now is like 1.5 volts, maybe? I should be able to get it where? All the way up to 3 volts, 1, 2, 3. So let's see if that happens. There it goes. Yeah, and a little above 3, which doesn't surprise me. The batteries might have a little output above 3. And I should be able to get down to 0, right? So yeah. And I can. Yeah. Once again, all the way up. Yeah, more down. Okay. So I'll put it, maybe I'll put it right in the middle. I liked where I was at 1.5 volts maybe. I don't know. I can see where the photocell is. It's tracking right along for me. Well, it's at about 2 volts, isn't it? And I think I know what to expect, right? If I shadow the photocell, it's in the position at the high side. So it's essentially where R1 would be if we call it R1 and R2. What do you think? Putting a shadow on there, is that voltage that's being displayed on channel 1, is that going to go up or down? Is it going to increase or decrease? I'm going to say the shadow will make the resistance go up for the photocell. It's in R1's position. It's going to take more voltage away from R2. So I think the voltage is going to drop. Let's see. Yep, it is dropping. You can get in there a little closer, right? How low can you go? I can't quite get it down to 0. It's hard to, light shines through your fingers. So if you had something more opaque, that's how they can measure the oxygen levels in your blood, by the way. They can send a little red light through your fingers. All right, so, but you can see I can control the voltage output. I can monitor the voltage output of my voltage divider with the photocell sensor in it, right? I could create a larger display. I mean, I don't ever go below 0. So if I want to use the whole screen, I could put 0 down at the bottom of the screen, couldn't I? I can also get rid of I can also get rid of some of this menu stuff. So let's do that just for fun. Maybe I don't want to go all the way to the bottom, but let's position 0 volts for both channels, just 1 block up. And now I can probably increase the scale. Maybe I'll make the scale like a 0.5 volt or 500 millivolts per block. I just get better resolution, So now, same range, but just more magnification, more magnified, right? Where's my potentiometer? It's at 0. I made it 0 counterclockwise just to keep myself sane. And I can go all the way up to a little above 3 volts. 0.5 volt, 1 volt, 1.5, 2, 2.5, 3. So I'm kind of framed in about 1 block up and 1 block down for my display area, and I like that. I could put the potentiometer right in the middle if I want to. I can set it wherever I want. And now I have my adjustability, my photocell when darkness comes, right? Voltage decreases or increases, or even just any kind of shadowing. So you can draw pictures now, right? This is the world's most expensive Etch-a-Sketch. You You could create a fake heartbeat, right? So many things you can do now that you have an oscilloscope in your hands. I'm just giving it light and dark, whatever. You get the idea. I like doing the slow scroll because it shows you what a scope is, I think in a really good way. It is just 4 voltmeters that we have here, 4 channels that can measure voltage. And then it displays it constantly, continuously. And so that's the time part. So in this mode that we're operating the scope, we have voltage displayed on the y-axis, and time is on the x-axis. And that's an oscilloscope for you. Now we can change that mode, and that'll be another topic down the road. But yeah, voltage and time is, you'll hear me say. But it is just that. It is just measuring voltage. That's what it does. It's got a lot of controls and a lot to learn. But in the end, this exercise, I hope, helps you see that it is just a really nice, elaborate voltmeter. You can display everything that's happened in the past, everything that's happening now. I can't display what's happening in the future. That's maybe the limitation. All right, so hopefully get that set up and prove to yourself, you know, what a scope is, and we'll take it from there. And while you have this very simple circuit set up, definitely fool with some of the scope controls just to help yourself get oriented, like the horizontal scale. I can go faster than this if I find this isn't really what I want. I could go faster, and now look, I can make those same changes, but they see how they just change. It's moving faster, so I can move faster and I can get that resolution. So I'm just varying, you know, the shadowing on that photocell. So experiment with that. That's the horizontal scale, telling you how fast you're scanning, right? At some point, it scans so fast, you know, you might. But see, I can make changes now. See how the frequency of the changes are going up. So in that case, I do need to scan faster to see them. If I was scanning slowly, so definitely, I mean, I hope this really helps you get the feel of what a scope is doing. Look, if those same changes were happening real fast, like this, I have a harder time seeing them. Maybe I can slow it way down, huh? Yeah, here we go. So look, now those same rapid changes, that would be the frequency, right? The frequency of change. It's pretty hard to make that out. But if you're scanning fast enough, that those same frequencies, now that's a little too fast maybe, right? It's hard to see them on the screen, right? So you get the idea, right? You want to match your scan rate, how fast are you sweeping across the screen, to how fast the signal is changing. So try all different settings, you know, whatever else you can fool with. Start slow for sure. Where is slow? Sometimes I'm going the wrong direction. Well, and you just spin the knob until you get what you want. But yeah, you can definitely start slow so you get the feel that your circuit's working right. And you can try, of course, the different scales, vertical scales as well. So the scope is an instrument we'll just definitely get to be getting to know better and better. It is our eyes into what's going on in a circuit. And so, for example, as we make this simple circuit get to actually do something and become more complex, the scope is still our eyes into what's happening in the circuit. For example, that potentiometer could be providing a reference voltage, and when the light falls below a certain level, right? I mean, so here's maybe, I don't know, the sun's going down, and our sensor, because we're monitoring our sensor with the scope to make sure it's working properly, and the sensor is picking up the darkness as it occurs. And when it gets a certain amount of darkness, which would be perhaps right below that threshold, I know it's jumping around a lot, but for example, sun's going down, and or whatever is happening, but the sun's going down, and right now it would turn on a light because it went below the threshold that I had set. So you could adjust what darkness level a light turns on, for example. So we'll get there. We'll be adding more components to this circuit, but what I wanted to emphasize to you is it's still going to be this setup as far as your scope is going to be able to show you if everything's working properly. Where is your reference voltage? You can see it right on the screen. You set it here, but you can see it on the screen, and what's happening with your sensor in the voltage divider, you can see that on the screen too. So yeah, so the scope is just the instrument we use all the time, because of course electrons are invisible. You can't really see them, but you can see the results on the scope. When you get this working, show it to me. I definitely want to see it. It'll let me see that you got at least this far as your understanding of the scope, and not a bad review of the voltage divider too. So I'll show that to me. I'll check you off, and then I'm sure we'll be doing more scope videos in the future. This gets us started though.